Good afternoon. We begin again. We continue with our discussion of control charts. The examples that I have here, these are from services. As you know, there are two categories of our economy. We've got production, which produces physical objects like this, and we've got also services, like for example, teaching is a service, or getting a haircut is a service, or getting served in a restaurant also is a service. For the majority, I would say most of the things that we have around us, they are a mixture of products and services. And we therefore need to monitor both. We cannot just say we'll only worry about products and we could not be bothered about the service that is being provided. I mean, think of a hotel room that you walked into and you found that the drape was had wrinkles and the bed had some disorder there and the flowers were thrown all around and so on and so forth. And the soap wasn't there in the bathroom and the faucet was leaking or something like that. These are service quality defects, and these also need to be monitored. And to be able to do that, we also can use control charts. The moment you collect data and the moment you convert that into a message, which is like a graphic message, people start taking action. This is what we do on the production shop, and it's very easy. Get your measurements done, come up with your X bar chart, come up with your R chart, display it on the wall, and of course it's going to show you if the process is in control. That means if the variations are within that tolerance, or if there are exceptional variations in the process that you need to worry about. If you don't do that, the customer is going to end up with a lot of off-spec stuff that he's not going to like. This is something that can also happen with services. So you've got some examples. Nature of defect, of course, is different with services. These are not dimensions, these are qualitative many times. They are assessed differently. You look at some of the examples there. For a hospital, it could be the timeliness and the quickness of care. So he came to a place where they basically tried to do, they have a facility where they provide treatment, and it turns out that the timeliness and the quickness is not there. This happens sometimes in healthcare systems. Staff responses to different requests that you might be making, these also may not be there. Lab tests may not be accurate, cleanliness may not be there, courtesy may not be there, accuracy of paperwork may not be there, and so on. Grocery stores, what kind of things may turn out? Waiting time is a big problem. It's a big issue. And this thing can be monitored. The frequency of out of stock items, that also is something that one can look at quite easily. Quality of food items, cleanliness and so on. These are all going to be aspects of service that you'd like to worry about. Then airlines. If you look at airlines, most of us, these days we fly, and we might be losing baggages. There may be delays in flights. There may be problems with luggage handling, for example. There may be waiting times at ticket counters and also at check-in. And there may be lack of courtesy, which happens with some of the airlines. And I hope very much that they quickly realize this, or they just get out of that business there. Because my time is not to waste there and worry about the fussing of somebody there. Accurate flight information, this also is very important. And obviously, passenger cabin cleanliness, that's important, and the maintenance of the whole aircraft, and so on and so forth. Fast food restaurants, a lot of things are there. Again, waiting time and so on. So you can actually see as you go along, services also provide a lot of opportunities for control, for quality control. And those also could be done, if you wanted to, those also could be done using control charts. That could be done using control charts. So airlines, they could plot charts, grocery stores, they could also produce charts. Hospitals, many of them, they do produce charts, quality control charts. The same thing could be done by banks, and I know some banks that have very meticulous procedures for collecting data. These are on the quality of service, and they track these charts. These charts are displayed proudly by those people who are exceptional performers. They show that their error rates are near zero. Their problems in regard to counting money is next to zero. They are courteous, they dress well, and all those things. If they are there, obviously customers are going to be attracted toward that bank. So this quality will lead to definitely more business. That's why you cannot just say that I'll be plotting control charts only for manufacturing people. I'll be only doing it for people who produce widgets and gadgets. No, it's also true for service and experience. There are aspects of it that can still be monitored. So that's like another area where we could use charts. Charts, by the way, I did not give you this name earlier. Charts were invented by a gentleman, his name is Walter Shewhart. And Shewhart came up with this idea that there are variations. In almost anything there are variations. But it's the exceptional variation that we need to worry about. We need not worry about the natural variation of a process. because to change the natural variation of the process, if the application changes, then I may have to change the technology, and that may cost me a lot of money. But I need not really do that. I need not really, spend a lot of money in just trying to keep a process accurate and also precise if I use the right kind of chart. And those charts would be the X-bar chart or the range chart. These monitor the sample averages, or I could in some cases use the X-bar chart and the S chart, or I could use the median chart and the range chart, or I could use the X-bar chart for individual measurements. I could also use the moving ranges. These are things that you can find out. Now that you have understood what control charts are, you've looked at an X-bar chart and an R chart. I'm going to be showing you some more of those. The other charts are all very similar. The spirit is the same. Try to distinguish between exceptional variation and natural variation. The moment there is exceptional variation, this is when you'd like to take some action. And leave the process alone if the variations are natural. Because every teller knows that there will be some variation signature to signature. Same thing happens almost with anything that you do. When you make an omelette at home, does it always turn out to be exactly the way you'd like it to be exactly every time? If you need that, you've got to have an omelette making machine. And then you're using technology. That's going to cost you a lot more. And that happens sometimes when you got to standardize things, you might use a lot of automation. But most of the time, we need not really have perfect standardization. We'll tolerate some variation there. And for that, control charts are just fine. Because they are going to catch the exceptional situations. They are going to catch that. So same thing would apply to attributes data also. There we'll be using the P chart or the NP chart or the C chart or the U chart. And these displays show you exactly what kind of quality characteristics are going to be there that are going to be doing this. Okay, let's come back to the X-bar chart and let's try to see what we could do. Remember the formula that I gave you. I gave you a little formula and the formula was right there, if you remember. I have this formula there and that shows you how to calculate your X-bar quantity. It shows you exactly how to do that. X-bar is sigma xi divided by n. That's it. And range is even simpler. Max value of xi minus min value of xi. That's it. That's range. X-bar is going to help you monitor accuracy of the process and R is going to help you monitor the precision of the process. So we need both of them because we need both accuracy. We need both accuracy and also we need what we call precision. We need both of these. A process must have this and also a process must have this. Only then we'll have a process that is going to be a satisfying process. That's going to be fit to be used in normal use in business. Let's try to see what else we do. So we got these formulas here. Let's work with some real data. I have here, the first thing I have to do is, I have to set up the system in place. So I set up the x-axis, which is going to be your sample numbers, and I set up the y-axis, which is going to be your X-bar values. But I need something more. I need the upper and lower control limits. I need the upper control limit and I need the lower control limit. These are statistical limits. These are ranges that define the natural variation of the process. If a process, if an X-bar value seems to be either exceeding the upper control limit or going below the lower control limit, the variation in the process is too much. It is not something that I should be living with. I have to do some troubleshooting there. I have to remove this. So for that, I need the formula for UCL and the formula for LCL, the upper control limit and the lower control limit. How do I do that? It's not that difficult. All I need is, I need a couple of quantities there, and the quantities shown here are the average X-bar. That means a long range average of X-bar. And in our case, that turns out to be 82.5 kilograms. This being something that probably is looking at the filled quantity in a bag. And there are many such bags being filled, maybe fertilizers, something like that, or maybe cement. The average X-bar value is turning out to be 82.5. Okay. The standard deviation of this, when I do my calculation, I find it to be 1.6. Now, let me come back and let me remind you of a couple of things. If you look at the normal distribution will have, if I show it here, it will have some variation, and that variation is going to be shown like the bell curve, like this. This is the bell curve. And something we got to remember is that the average is going to be at the midpoint, no problem, and that's mu. Then there is going to be variation that's going to be slowly decreasing as you go to this side, and the frequency is also going to be decreasing on this side. It turns out if you look at the distance of 1 sigma, and if you look at 1 sigma this way and 1 sigma this way, this area contains 66% of all the points in this area. So this area here, this area is 66%. If I change this, if I make it another sigma, let's say I came up to this point here, that's like another sigma from here. So from the midpoint, I'm now 2 sigma away. So from the midpoint, I'm 2 sigma away, 1 sigma and 1 sigma. This distance from here to here, this will contain 95% of the area under that distribution. And of course, if I go out to the far end, and if I come to this area, which is like another sigma away, 1 sigma here and 1 sigma here. If I go all the way out there, then the area that is between these two extremes, and I'm going to be approximately drawing that for you, this distance here, that covers 99.7% of the total area. Now, if there is some random variable, call it diameter. I've got an average diameter there, and this is my random variable x. These two ends are rare. These are rare values of x. These are rare values of x. To find a value of x, I have to really go through 1,000 samples, and perhaps 1 or 2 items will find falling at this end or this end. These are rare values of x. The more likely values of x are right here. These are the most likely values of x. These are going to be the most likely values of x. These are going to be rare values of. So this is rare. Also this is rare. Why I say that is that the control limits are set. The control limits are set exactly at this rare limit there. So there is the upper control limit. Upper control limit is here, and the lower control limit is here. Anything beyond this is rare, and anything beyond this is also rare. Therefore, when I plot my control chart, and I find points coming over here or coming over here, that is no more explainable by the natural variation of the process. Natural variation stays right here. But the moment I find 1 or 2 x bar points there, 1 or 2 x bar points there, and all I have to do to understand this is to turn this sideways. And I do it just by putting it like this. And you can barely see on the screen, you can see the lower control limit and the upper control limit. Or let me just do it this way. Now you can see the upper control limit right there and the lower control limit right there. If the data points that I plot, if they turn out to be here, here or here, or here, or here, no problem there. And let me try to make them a little dark for you. And I'm just going to be making them dark by filling them in green. So there is a green point there, there's a green point there, green point there, green point there, green point there. These are all within our natural variation, no problem there. But by golly, if it turns out one of the points is here, or one of the points falls here, that is way below the lower control limit, it's way out there. This is something that requires investigation. And also the upper point here, it requires an investigation. Now just remember one thing, I drew the upper control limit 3 sigma away. I drew the upper control limit 3 sigma away from the midpoint. So from midpoint to this point, it's 3 sigma. And because this is x bar, if it is x bar, it will be 3 sigma x bar. And the same thing goes this way. The lower control limit is also 3 sigma x bar below the midpoint. This is the midpoint. Midpoint is the middle point there. So my control limits are located just to indicate the beginning of those rare events. And this is exactly what I've got on my screen here. Notice my screen here, I've got the red line going as upper control limit, I've got the lower line going as lower control limit. These turn out to be the limits. Within that, I've got my natural variation. Anything beyond that is something, is a region that I need to, if a point falls there, I need to investigate the process. How do I find them? All I have to do is find the value of sigma x bar, multiply by 3, add that to the average, just like I did it here. Just like I did it in on my sheet here. On my sheet, I have my midpoint right there, which is the x double bar value. The x double bar value is right there. The overall average x bar value. I added 3 sigma x bar and I got my upper control limit. And I subtracted 3 sigma x bar, I got my lower control limit there. That's exactly what I've done there. Notice here it says 82.5, which is my average, grand average, plus 3 sigma x bar, and I end up with 87.3. And I do 82.5 minus 3 sigma x bar, which turns out to be 77.7. These are the values of my lower and upper control limits. That's all the calculation I need to do. Of course, to be able to do this, I need to find the value of sigma x bar. And there are some shortcuts to do that. So again, this is the normal curve which I just showed you earlier. The region that is near in the vicinity of the mean of the average there, the grand average, those are all okay events. The ones are rare, the ones that are rare are going to be the ones that are going to be beyond the 3 sigma limit. And those are the ones those are going to be our rare events, and those are the ones that need to be investigated. So, if a process, we say that a process is in control, if there are no sample points are like x bar values or r values beyond the upper and lower control limits. Most of the points are near the process average. About equal number of points are above and below the central line, and points appear to be randomly distributed when I look at the chart. And if I do that, my distribution is going to be mostly in this green area, and that's going to be the process in good control there. Now, there is something written up here, notice the central limit theorem, which basically says this: no matter what kind of raw data you have, the moment you calculate your x bar value, it will have a normal distribution. And because it will have a normal distribution, I can use the 3 sigma x bar. So, the average plus 3 sigma x bar and the average and 3 sigma x bar below it, those as control limits, because the distribution x bar is normal. That's the reason for us actually even constructing a subgroup that is of some size. Subgroup is basically this sample. I have individual data points, and what I really do is I collect a few of these data points and I look at their average. That's how I calculate my x bar value. And that's something that we'll be doing again as we go into our example. So, my raw data has this distribution, and my x bar value will have a shrunken distribution. It will always be normal. In some cases, of course, even the raw data is normal, then of course, this definitely is going to be normal. But even if the raw data is not normal, when I construct my x bar value, which is x bar is now the average of n number of x measurements, and we'll do some examples and you'll see how that is being done. So, the control limits actually turn out to be narrower than specification limits. The process variation is going to be much wider by itself, raw process variation. But the process variation in which we've got interest is the variation of the x bar quantity or the range quantity, and that's got to stay within these control limits. So, I must use the formula for UCL, I must use the formula for LCL to know exactly what this range is, where if x bar values lie within this limit, of course, then of course, I've got no anxiety at all. After I've plotted the chart, and these are points that have actually come about as I started running the process, I collected data and I calculated this is the first x bar quantity that I found, second x bar quantity I found, third, and so on and so forth. When I get to this point, I find that the point has now gone beyond the control limit. I should stop the process because the process is now out of control. It's not under the influence of those small chance factors only. There are some unusual factors that have impacted the process, and the chart is telling me, please stop the process, take a look, do an investigation, and then do it. then move along with this. And of course, this is the repeat of the same thing. I'm again showing the variation, and I'm showing you a couple of data points that are out of control. The same principle basically applies to the X bar R chart, the P chart, the C chart, and so on. All these charts, they are due to this Dr. Walter Schuhart. He's the one who actually conceived this idea, and he came up with this idea of separating between assignable causes or the special causes of variation from what we call the chance and the novel causes of variation. This is something that we got to figure out. And how do we figure them out? We figure that out by just plotting the chart and finding out if there are any points that are beyond the control limits. The moment a chart shows points which are beyond the control limits, either above the upper control limit or below the lower control limit, stop the process. Don't continue with your production. Go and take a look at the tools and a variety of things, and I'll show you how to do that. Once you've done that, you basically remove the factors that could have caused the process to actually go out of control. Special causes of variation, these are the ones that actually are the assignable causes of variation. And there are many examples, and as experience grows, we find that we are able to tell between the special causes and the common causes of variation. That's not going to be that difficult. Now, something more we have to actually tell you. Notice here, I constructed my charts using the X bar quantity. X bar quantity. This I used to try to see if my accuracy was okay. Then I could also look at the variation of the process, and for which I could really construct an S chart. This could give me an idea whether precision is in control. But you remember the formula for S, which is a little complicated, is square root, and then we do sum xi minus x bar, and then I do I equal to 1 to n, and I divide this whole quantity by n. I take that square root, that is my S quantity. This is a rather complicated formula. If you are doing this in production, even if you had a calculator, with you, it would not be easy to execute this. So what have we done? We've said we will probably use the calculator to find my X bar quantity only. But we use, in place of S, we use range. And range is just max xi minus min xi. And this will do the same job. It will also let you control precision just as S does. This will do the job just as good. So in fact, I can control accuracy using X bar chart. I can control precision. I can monitor precision by looking at the R chart. What is the link between these two? You might just say then, is there a correlation between these two? Let's look at some real data. I have on the screen here, the top chart is the S chart, the standard deviation chart. I've got my samples here, I've got the values there. For the same data, I calculated range, and they are like this. And notice how close these two are. In fact, if you do a correlation plot between them, if you do a scatter diagram, that correlation turns out to be like 0.99 or something like that. That's really, really good, which really means in place of using this complicated formula to find my standard deviation, I could just find R and use R to monitor precision of the process. That I could do quite easily. So in fact, the common practice is plot the X bar chart and then plot the range chart, and you carry along with this. How do I construct these charts? Well, you have the formulas which are shown here, and finding the grand average of X bars is not that difficult. The overall average, which is I'm showing here, I'm showing that by showing you the average of sample means. Sample means are little X bar values, and I found X double bar, which is the average of these sample means collected over some history, maybe last 1 week's production or something like that. So I've got an idea of X double bar, which I use to find the upper control limit. I should really be doing X double bar plus 3 sigma X bar. That's what I should be doing. Very fortunately, other people have worked on this. Other people have worked, they said in place of doing this 3 times sigma X bar, I can use a quantity called A2, which is a multiplier, a constant that depends on sample size n, and R bar, which is the average, just like I found a grand average of averages, sample averages, I find the grand average of what we call ranges. I use that as R bar. I can use this formula to find my upper control limit. I can use this formula to find my lower control limit. So, what are the new constants I have used here, new quantities? K is of course sample size, number of samples I have got, to calculate my X double bar. R bar is again the average of the different R's that I calculated for the K samples that I took. A2 is a quantity that will depend on sample size, and I am going to show you how to do that. Once I know those, I have got my UCL known and I have got my LCL known, and these can be clamped down right on the control chart. Let us try to do some of these calculations. Let us try to do this. Let us try to see if we could come up with the quantities to be able to do our calculations here. Now, let us first become familiar with the table itself. Samples are 10 samples have been collected. So, sample number 1, it has got 5 individual data pieces. So, these are the X values. These are the X values. X1 is 5.02, X2 is 5.01, X3 is 4.94, X4 is 4.99, X5 is 4.96. Okay, let us write them down. In fact, what I could do is I could go straight to my calculator. And I am now using my calculator, and I will just read off, I will just look up this table and I will use my calculator which I am showing on the table here, and just watch my fingers. I am going to be using this. So, the first quantity is 5.02, 5.02 plus 5.01 plus 4.94 plus 4.99 plus 4.96, and this is going to be the average. So, I have got the average that I have got 24.92. I divide now that by 5. So, I divide this by 5 to get my first X bar value. What is the quantity there? 4.984. I am a little more accurate than the table here. The table shows the value of X bar to be 4.98. Let us now try to find the value of R. How do I do that? I locate the maximum value of X in that sample there. What is the maximum value? 5.02, 5.01, 4.94 and so on and so forth. So, this guy is maximum. So, I enter that quantity there, 5.02. Now, this is the max X value. What is the min X value in this? It is 4.94. So, I do minus 4.94 and I do an equal and I get 0.08. That is the value of R. So, what have I got here? I have got two quantities there. I have got my X bar 1 equal to 4.98 and I have got R1, this is equal to 0.08. These quantities are for the first sample. I will do the same thing for second sample, third sample and so on and so forth, and you can notice here on the screen I show here the different values of X bar that have been calculated by doing that. This is X bar 1, X bar 2, X bar 3 and so on and so forth. If I take the grand sum of all this, that is this 50.09. If I take the grand average of all these, I have got 1.15. So, let us try to find now X double bar, which is the grand average of all. So, I again come back to my calculator, and what I do here, I use my calculator in a very special way now. I do 50.09 and I divide that guy. How many samples are there? 10 samples. Divide that by 10. And that turns out to be 5.009. 5.009. So, my X double bar is going to be 5.009. What about R bar? How do I find R bar? All I do is I look at the sum of R's, and that's 1.15. So, I put in 1.15. I divide that by 10. So, my R bar value turns out to be 0.115. I have these two key quantities that I'll be using to construct my UCL and LCL. The only things that I need now, I need some constants, and we'll find out what those constants are. And I need to remember something called sample size. What was my sample size? For this problem, my sample size was n equal to 5. N equal to 5 was my sample size. I'll be needing this quantity to be able to find those, the constants A2, and there will be some other constants also in trying to find the control limit for the range chart. That I'll be doing that. So let's turn the page over and let's see how they found their quantities there. And look at this, x double bar. He had 50.09. He divided by 10 and he got, in his own approximate way, he found 5.01. And I found, of course, 5.009. That's the only difference there. Then, with this, he also has calculated his R bar. And R bar, of course, luckily coincides with us. R bar, in his case, is 0.115, which I see there. I see 0.115, no real problem there. And I have to multiply that now by this quantity called A2. And we'll try to find the value of A2. We'll try to find the value of A2. A2 can be found once I know n. So remember our n is equal to 5. From this I can find my value of A2. And for that I just have to go to a particular table, a particular statistical table that will give me the value of A2. And I'll get to that table in a minute. But the anchor is going to be my sample size n. Once n is equal to 5, I'll be able to find my value of A2. The moment I find the value of A2, I can come back and plot it, and I can just plug it in my thing there. And notice he's found the value of A2, and I'm going to be finding that also for you. I end up with my value of upper control limit for the X bar chart. I do the same thing and I just flip the sign here and I find my quantity for my value for the lower control limit. And of course, then I've got my lower and upper control limit and I've got all those X bar values. Remember, I have the X bar values here. I've got my X bar values there. I also got my range values there. Now, because I've got my control limit there, it's very easy for me to plot this chart. What have I not found so far for you? I've not found the value of A2. A2 is something that I'll have to find out from somewhere. And A2 is found from, in books of quality control, they provide a special table there and they tell you, please indicate what is your value of n, the sample size. Once you tell it the value of n, they will tell you what this value of A2 is going to be. A2 depends only on n, the sample size. So we'll be able to do that. Once we go to the right table there, we'll be able to find the value of A2. But returning to the chart again, notice here the chart has all the things there. It's got the upper control limit, the lower control limit, the midpoint there, sample numbers here and so on. Now this chart is ready now to monitor production beyond this. Beyond sample number 10, I could continue to have the same control limits and I'd keep plotting the new points there which will probably fall there and so on and so forth. And let's hope that they will not cross the limits. And now, there are some other issues which are brought up once in a while. What is the chance that the chart is going to give you a false signal? That is done by using this concept called average run length of the chart. When you've got the alpha is the chance of what we call type 1 error using the control chart, which is like getting a false signal out of the chart. And a false signal will come when you get a signal out of the chart, which means you find one point going out of control, even if no sign of causes have really disturbed the process. So the process is still fully under the influence of random causes only. But because of this statistical exception, because remember the normal curve had tails that went beyond the 3 sigma limits, it's those tiny, teeny-weeny tails that are there. They also cause sometimes this natural variation to push out a few points beyond the control limits. And that will happen at this rate, alpha by 2 on the high side and alpha by 2 on the low side. So therefore, there is a little formula there which tells you average run length, that is the average number of sample data points that you need to plot, that you should plot before you should expect to see a point that is out of control, even if the process is in control. So that's the chance of my making a type 1 error. Type 1 basically means a false witch hunt. You think that the process is out of control, actually it is in control, it's under the influence of random causes or chance causes only. And just under the influence of these chance causes, it has pushed out a few data points that are beyond the control limit. That's all. Nothing else. No, nothing else has gone wrong with this. But obviously, if the normal chart shows you that it has gone beyond control limits, and we've got many examples of that, and we'll see some more examples as we go into this. For example, let me just bring up one or two examples. We had seen them earlier. An example is going to be this one, for example. Control limit exceeded. Control limit exceeded. These are going to be instances when you got to stop the process regardless. Don't second guess. The moment the chart has gone beyond control limit, stop the process and go to something that is called the reaction plan, which is what you construct using the cause and effect diagrams and so on. But then go through your full checklist, full list of checklists, and check everything about that machine, just to make sure that you will not really end up with that problem being there and you think everything is in control and you'll end up producing products that are off spec. Let's take a look at one or two other items which are related to this. There are certain things called warning limits which are put 2 standard deviations away. You know, the control limits which are like the action point, those are put 3 sigma limits away. But sometimes people also put a limit at 2 sigma limits away, 2 sigma limit from the base side. These are warning limits. They actually tell you where we are finding too many points in the vicinity of the beyond the 2 sigma limit, which actually is saying perhaps something is creeping in, some problem is creeping in. And it's just a warning limit. It's like the amber light. When you're driving on the road, the amber light appears, you become cautious. So if a point goes beyond the 2 sigma limit, you're in that amber zone there. Just be cautious. Look out for your tools and make a few checks, just to make sure nothing really is going to break down in a little while. And of course, the bad thing is when you get no signal out of it. The process has actually changed, but you get no signal out of it. I have exactly the same formula again here. I show here by showing you that how to calculate x bar, how to calculate r, and how to get the control limits. And of course, again the issue is that of knowing what A2 values are, and A2 values are now found by this table here. It's got a few other constants also which are used for other purposes in drawing control charts. But notice here I've got sample size here in column 1 and column 5. Column 1, row 5 gives you the value of A2 in column 2, which those guys took to be 0.58. The true value of A2 is going to be 0.577. So since our sample size is 5, I can use this quantity as the value of A2 and go back into my formula and plug that in there, and I'll end up with my control limits here. This is the way you calculate your control limits for the X bar chart. I have a very similar procedure which I use for controlling my for plotting the R charts. I do that. And here's an example again, just like the example that we saw there. Here's an example again, and you can verify that the sums of these columns, this sample number 1, sample number 2, and so on. There are 25 samples collected. These are the raw values, and here's the value of X bar right there, and here's the value of R, and you can verify, for example, 6 minus 4 is equal to 2, which is the range for the first one. Similarly, range for second one, third one, fourth, and so forth. Once I get all these things, I can calculate the totals, I can calculate my X double bar and R bar, and I can use the same formula and I can calculate the thing. And here are the calculations, and if you want to see the chart is right there. So the same data, the data that I showed you this time, those data have been used to set up the control limits, and now of course the 2 charts are there. To remind you again, we need both the mean chart, which is the X bar chart, and the range chart, because we are concerned about 2 aspects of the process. One is accuracy, the other is precision. Both of these have to be, certainly when the data quality is measurable, I need to know if the process is producing items which have their values pretty close to the target value, and this is an indication of accuracy. And precision is when the production is such that most of my production is consistent. That means regardless of which cap I pick, they will fit. they will fit. In actual assembly, they will fit because they're all pretty tight to each other. The process is precise. Here's another example, and you can try that example. You can look at the numbers there, you can freeze that screen there, and you can check it out. And this again will give you your values there. No real problem there. In some places, I have shown you how to do your X bar chart and how to do your R chart. In some cases, I have also shown you how to do the S chart, and they turn out to be very similar. Here's the range chart, the formula is right there, and I followed the exact same procedure, and I ended up with the value of R. I find R bar from there, and of course, I calculate this. Now, something I want to point out here. Remember, we used A2. We used the quantity A2 to A2 in our case turned out to be 0.58. That is what I used for my X bar chart. And for my range chart, I use something else. I use some other constants, and these constants are going to be D3 and D4. And what is the formula for the range chart? UCL range, it's D4 times R bar, and LCL R is going to be D3 times R bar. These are the formulas. These are the formulas that are utilized in constructing a range chart and putting control limits on it. And that's what they have done on the screen there. Notice. Again, where do I find my D3 and D4? I go to the same table. And I have their D3 value and D4 value. What are these dependent on? Again, they are dependent on sample size n. So, if I know my sample size n, which in our case was 5, I find that the value of D3 is 0 and the value of D4 is 2.11. Let's go and see what they have done. They use the value of 0 to find the lower control limit. So, the lower control limit for the R chart turns out to be 0, and for the upper control limit, they have used D4 times R bar, and they use 2.11 for D4, and they end up with the upper control limit there. So, these are the ones that then become our control limits there. Here's the chart. Here's the chart that actually was constructed using the same data there. And again, there is an example, and you can again verify your construction there and get the thing. So, it's like a range chart done, another example of what we did before. These are all going to be examples, and you can flip through them back and forth, and you can actually verify that the numbers are right. And what we have to do is, we have to now move toward what we call getting signals out of the chart. How do we get signals out of the chart? How do we find these abnormal patterns? They are going to be found like this. Both process average and process variability must be in control. Process average is your X bar, process variability is your R or range or standard deviation S. It's very possible to have a very tight process with very good precision, but the average may be off. This is no good news. Or it's also possible that the average is right there, but you've got wide variation. Both of these are problem situations, so I've really got to use, I cannot just say I'll be only using X bar chart in my plant. Or you go to a manager and all you see is you see a range chart plotted, no R chart, no X bar chart. These are not going to be good situations, because you'll have control only one aspect of quality. You'll have either control of the accuracy of the process or the precision of the process, but not both. But in real life, we need control on both. You need to have accuracy there and also need to have precision in the process. So, therefore, we got to have both of these charts. Now, what happens after you plot the chart? You find some unusual patterns. One very simple signal that you get out of a process is that one of those data points went beyond the control limit. That's like one signal out of a control chart. It can happen on an X bar chart, it can also happen on a R chart. Both of those charts, they can actually give a signal. So, I can either get an X bar chart giving a signal there, or I can get a range chart giving you the signal there. Both of those are possible. What we have to do is, we have to see, can I get more signals out of the same chart? I need not really wait till I get a point beyond control limits. There are a number of unusual statistical patterns that are also visible on control charts, which are under the influence of assignable causes or these exceptional causes. What are those examples. What are those examples of those patterns? Unstable process. An unstable process will look like this. A process with trend will look like this. The blue lines are the control limits, and look at the way the process is moving. It's slowly rising and rising and rising, and suddenly it will go beyond probably what is acceptable to us. Or there may be cycles. These may be two guys, one guy works day shift, the other guy works the evening shift or something. And their settings are different, and therefore they produce this cyclic behavior in the control chart. Or there may be a genuine shift in the process. This is like, if you've been in a truck, for example, you'll find the same truck is used or the same bus is used by various different drivers. And every time the driver changes, the new driver comes in and readjusts the seat. In fact, I did that when I was using this chair, because the instructor who came before me, they had a class before me. He had made this pretty low because he's like a big tall guy, not a very fat, but a very tall person. So he did not really need that much height in the chair itself. But when I came in, I'm like about 7'2". So I need some lift. No, I'm actually 5'4". So I needed some lift. So I adjusted the chair. Now this, if it is done, if you watch the height of the chair at different hours in this studio here, you'll find that the height is changing like this. It is going up and down like this. And that is exactly a shift in the average. That's the lowest pattern. This is something also, something we'd like to see. So the same kind of abnormal behavior is there. You see the chart going from one side of the midpoint to the other side of the midpoint. This is also a signal that something is happening with the process. Or a trend going up or a trend coming down. These are also, again, abnormal patterns. Or too many points on one side of the chart, which is one side of the midpoint. These are also exceptional points. So even if the control point, even if the point that you're trying to plot has not gone beyond control limits, but you notice one of these exceptional situations, you need one of these things, stop the process. Stop the process, because it may be too late if you wait for a real point to go beyond the control limit. It may be too late. You might have produced a lot of useless production. You may have produced a lot of widgets that have no real use. They are not going to be fit properly, because the pattern has already shown that there are some unusual variations. And even that point going beyond control limits is an unusual variation. These are the other patterns that actually also give you unusual variations. Sometimes people set up zones on their charts, and they say, 1 point beyond zone A, bad news. 2 out of 3 points in zone A, for example, that's also bad news. And so many points in zone B and so many points in zone C. If these things started happening, these are also unusual patterns. And these are patterns that one should look out for them, and we should try to see what could be done to try to prevent them. These are all going to be abnormal patterns. Like some examples are given here. 8 consecutive points falling on one side of the central line, or 8 points running up or running down. These are also unusual patterns. 14 points alternating up and down. These have all been found by, in this case, the AT&T company. And they have set up a lot of rules besides the point going beyond the control limit. These are additional rules. So they give you additional power, truly additional power to stop the process when the process is not gone out of control yet, as far as looking for a point to go beyond the control limit is concerned. Or 4 out of 5 points in zone A or zone B. Remember these zones? So there is a rule based on the construction of these rules, and that says if 4 out of 5 points are in zone A or zone B, that means there is an exceptional situation. You should stop the process and do something. What do you do? What do you do? You've now found out that yes, I need to take some action. I've done my calculations. I've plotted my chart. I've got all the control limits and everything done there. I've got my chart going. I've got absolutely nothing I've done wrong. And I now find there are some abnormal behavior, abnormal points. Now, I've given you a sheet here which says is the reaction plan to use when the process is out of control. How do you know the process has gone out of control? Well, those exceptional patterns or a point beyond control limit. Then what you do is, well, before that you got to do some work. You've got to prepare this reaction plan. What you do is, you sit with people, those who are actually familiar with the process, and you construct, look at the top half of the program, of the page here. You recognize this tool here, this is your simple fishbone. And the fishbone says there are certain conditions that will drive your process beyond specification limit. And many times these are the factors that also make the control charts go beyond control limits or show some exceptional patterns and so on. Now say you have found a point beyond control limits. Stop the process. Pull out your checklist, and your checklist is this. This is your checklist. And very systematically go over the items, and I've listed them out here. So you notice the factors here, the causes that might have caused, in this case, impurity to go beyond specification limits. Impurities must stay within some specification limits. The first factor is this, error in calculations. So probably some calculations were done using a calculator to adjust maybe the quantity of catalyst or something when this process was running. And perhaps somebody pushed the wrong button here and it created a number that turned out to be different. And if that thing happens, that's actually not so good news. If you've got a wrong data there, that has now gone into your process and it's caused this variation there. What you do is you recheck your calculations. So I've listed that because it was in the cause and effect diagram. I've listed that, and I do the calculations there, redo the calculation, and I turn to make sure, I in fact turn to the process and make sure that I've done all the rechecking and so on, and I mark right here, have I found the problem? Calculations correct? Yes. That means I need not really worry about this factor, then go down to the next one. New batch of catalyst added, is that true or false? That could have caused the problem. This is also not a problem. That means no, it's not a new batch. Too much quantity added or too little added, check the batch records, check the sheet, look at the scale and so on. Make sure the scale was calibrated, all those things. If that is happening repeatedly, then of course you probably are missing on gauge R and R. That is something you probably should not do. Particularly if you're trying to be a Six Sigma production process, you should not really do that. So you go over these things, low purity catalyst, that also could be a reason for this, incorrect temperature, incorrect pressure, error in testing, or bad lab chemicals. So you're actually getting a bad test coming out of the laboratory. This is our checklist. So whenever we've got an exceptional situation, pull out this checklist and you start very systematically going over 1, 2, 3, 4 these items and just see the results of your investigation. If you've done it properly, if you've done it diligently, you are very likely to catch the problem. If the cause and effect diagram has been constructed with a lot of honesty and by looking at previous history, previous problems and so on and so forth, not many other things are there that are going to be beyond this. Most likely your problem is going to be one of that of calculations wrong, or you added something differently, you added a wrong quantity or something like that, or maybe a new person came along or something like that, but something that you can put your finger on. This is called assignable. The very fact we use this word assignable means that the chance of a point, and now I go back to my, this fancy diagram there, the chance of a point to be found beyond the control limit, either here or here, I can go back to the root of it. I can go back to the what we call the checklist there, and I can put my finger on the source of it. Once I've done that, the battle is half over, because I've found the culprit. The next thing I do is I basically take care of that. Something that is important for us to also remember when we are doing control charts is the sample size. Normally speaking, when you're calculating these quantities, the X double bar and the R bar and so on, take 50 to 100 data points, 50 to 100 samples. And as far as these are going to be for attribute charts, for the P chart and the NP chart and the C chart and so on. If you're doing, basically if you're looking at the variables chart, what should be the size of your N, which is like the subgroup of items that you decide to pick every time. So I collect so many data points and I average them out. I calculate one value of X bar and one value of R. How many data points do I need? It should be between 2 and 10. If you do that, it will be very easy to go to the table there and find your quantities. And you could start with a process that is like this. I started a process that was like this in Singapore, and we did not even have the cause and effect diagram. It took some effort for us to go down to a stable process. This was not stable there. Look at the point out of control. This was more like the general story. Almost every other day we had a problem like this. Then we understood that, we did a lot of studies and so on. Then we got to this. What is the problem with this one? Notice here the target is off. This is still target is off. So we had to restore the process to the correct target. And this was done using design of experiment. That is a very powerful method to try to adjust the process. And that is also a key tool used in Six Sigma. Especially if you remember Six Sigma DMAIC, D-M-A-I-C. The I, or the improvement step, uses design of experiments. And here is also an improvement. And here what we got is, we've got the process there, which is fairly wide. And I've got to, first of all, control the precision. We also control the, we got to basically restore the accuracy of the process. So I start with an out of control process, I bring it in control, then I tighten it and I restore the accuracy of the process. This is the improved process. In fact, this is the way these Six Sigma projects move. They start with a very, wide sort of variation, and then slowly and slowly, as they understand the process, they apply the right tools, one of which would be your DOE. But for monitoring a process, control charts are the way. Because without control charts, we wouldn't know how we are doing. There are some other things that we'll be doing. We have other types of charts. We have the P chart and the C chart, and we'll be looking at what those charts are in a couple of minutes. Thank you very much. We'll continue in just a short while with the next session. Thank you.